Now we come to our last speaker of the day. It's Dr. Josh Loukus. Thank you very much for joining us. Dr. Loukus is the president at REL in the United States, in Michigan, I believe. Dr. Loukus provides ideation, inspiration, and perspiration to the development of world-class equipment. He says the REL branded equipment has developed and maintains a top-tier reputation for robustness and quality. REL's relentless innovation maintains a reputation in high strain rate material testing, very relevant to today, wet process automation, and ultra-high output LED lighting marketplaces. Dr. Loukus has 7 issued patents and 30+ patents pending. He received his bachelor's degree in mechanical engineering from Michigan Technological University and his PhD in mechanical engineering. At that, I'll pass over to you, Josh.
Thank you very much. I'm Josh Loukus. I'm with REL. I developed this with Trey Leonard with Mississippi State. Those guys are down south from us. This is just the world map showing where we are relative to you guys. It's pretty early in the morning over here, so we were able to wrestle ourselves out of bed and participate. We're excited to show the kind of stuff we do. So again, the presentation is on the Serpentine bar technology. So Mississippi State developed this technology as a way to fold our Hopkinson bars on each other. So a couple of gentlemen I work with, collaborate with here is Luke Luskin and Adam Loukus. They're part of this work as well. So just some background, you heard in the introduction, we do specialize in, building split Hopkinson pressure bars. I did my PhD with Dr. Subash, built a lot of apparatuses and that sort of thing at Michigan Tech during my work. He's now at University of Florida. This current work, this Serpentine waveguide, as we call it, is to address the intermediate strain rates that are, more and more important from the previous presentation, impact experiments. 500 per second is very, kind of a high strain rate regime for a lot of different human considerations. Split Hopkinson pressure bar, we can get up into the thousands, but it's not quite as useful. So the Serpentine waveguide allows us to fold our bar into a smaller space to basically make it more accessible to labs that don't have, huge spaces. So we're hoping to be able to package this technology and instead of a 40-foot system, package that down into a 10 or 15-foot system. So we'll go through some of the background. This is a system we built here. On this end here, we do our launchers. Everything's automated. We have our computer system. There's a Shimatsu camera. This system here went to Callaway Golf. They do a lot of material research, obviously, on golf clubs. We're starting to leverage this technology into the commercial sector. It's not just the testing space. The types of tests we do, split Hopkinson pressure bar, we do compression. Here's the top. You're looking at 10,000 per second. Torsion, we have a torsion system. We do about 3,500 per second max strain rate. And then we do 4 different brands of tension. And they range from threaded specimens, which is this third one down, with a flat cross section, round cross section, and then we also have 2 grip systems, one for a steel bar and the other for aluminum bar tension testing. So as everyone knows, it's done split Hopkinson bar testing. The properties of your grip system are very important, and impedance match is important to deciphering your data. Materials we test, here's just an aluminum alloy. We've done a lot of carbon fiber work. Again, tension is gaining a lot of popularity in this type of work. 2D image correlation, we have a software that we give away. It's called SurePulse on our website. Sorry about that. where basically we include the 2D DIC strain map. So if you have a high-speed camera, you can use the software to see your material failing, as opposed to using a reflected pulse. So background, obviously, Hopkinson and Kolsky did a lot of work back in the 40s and 50s. It's getting popular because of the invention and the price reduction of high-speed cameras, where we can actually watch our videos in real time. So again, this current work, here's a couple of huge systems that are used for doing long duration waves. And this picture on the right is at Ohio State University. I want to say it's probably about 80 or 90 feet long. We built a system for ARL that's about the same. Just if you want to do longer duration stuff using wave propagation, you need a long system. Let's see here. For some reason I'm froze up. There we go. So a lot of fields of physics have come up with a way to fold their technology. Your antennas for electromagnetic stuff, your microwave resonators, folded horn and acoustics. There's a lot of neat techniques for packaging, for longer wave durations. So that's the intent of the Serpentine bar, is to do the same thing in split Hopkinson bar, or long duration impact loading. So Whittington down at MSU basically came up with the prototype for this Serpentine bar technology. On the right is his prototype, where basically he was able to take these concentric tubes, impact a rod, and he's able to fold it back on itself. So we came in to commercialize this, or build something to see what kind of properties we could achieve with this type of technology. So on the left here is just some strain results from some stress strain tests that were done under compression at Mississippi State University. So again, the whole idea is to take these tubes and fold them back on itself. Now the trick is to be able to do that and maintain mechanical properties. So we came up with a threaded concept at REL, and we did some testing to see what kind of stress we could impose on the bar itself. So just so we're on the same page here, here's some standard striker bars or waveguides. These are what we use to impact in Hoppy bar. This is a large diameter striker in the middle. We use polycarbonate for high displacement polymer testing. We'll use concentric tubes. This has a hole in it. This is a tension striker. And then these are some smaller compression striker bars, and we'll show you the testing configuration, how those are typically used. So this Serpentine bar technology, basically we're going to take these standard waveguides and then try to create folds to keep the package length as short as possible. Anyone that's done testing realizes different applications. We use different tricks to increase our pulse duration. One of them is pulse shaping. So what you see in this picture here are these are pulse shapers for tension testing. So this would go on a collar, and then these are your standard, copper and some polymeric, pulse shapers for doing compression testing. Those just go on the end of a bar. So here's the compression launcher, just so the type of launchers we build. So at this interface right here, here's your impact striker bar. Is typically a solid bar in a compression test. You'd put your pulse shaper at the end here and create a stress wave in your incident bar. So there's gas pressure inside of this chamber here, and we got a quick release valve to basically accelerate the striker bar. So the systems we have, we do that automatically, and we achieve our launch velocities up to whatever the yield strength is of your incident bar. So for aluminum, we limit the impact striker bar velocity to about 150 feet per second. And if you got miraging C300, we're at the 350 feet per second as a limit. Otherwise, you're going to yield your incident bar and your striker bar. For tension, we use what's called a hollow tube, and we accelerate that along the axis of a bar, and we impact the flange on this end. So basically we just take our same gun and reverse it and put a hole in it and use that to launch hollow tubes. So pretty straightforward, pretty robust system. So what are we trying to do? We're trying to create a long duration pulse, right? So long in hoppy bar world is, you know, a millisecond is a long time. So we deal with hundreds of microseconds typically. In steel and aluminum, basically it's 10 microseconds per inch of striker bar. So if you want to create, you know, a 350 or 340 microsecond pulse, you need something 34, 35 inches long. So what we're showing here is, you know, just a pulse done with a, you know, a long striker bar. And you can see it goes down, that's compression. So if you wanted a longer pulse, the typical approach would be, well, just get a longer bar. So as you can see, the system scales pretty directly with, you know, if you want a longer pulse. If you wanted 1,000 microsecond pulse, that'd be a, you know, 100-inch striker bar, which again, we've built for different institutions. But systems get long and unwieldy. We can also do this the same length pulse we do in tension. Again, this is a 32-inch for the same, you know, 300 plus microsecond pulse. So these are unfiltered responses. Just you can kind of see your Gibbs phenomenon here, and it kind of dies out as it goes. We typically don't filter our pulses. We wait till we do our data acquisition. We do all the filtering at once. So these are just raw pulses here. So the idea is to take that long tube that's 34 inches. Again, this is our current work, right? So we did is we folded it up and just into a package that we could machine here at our facility. And we actually went with a 51-inch long serpentine bar and fit it into an 18-inch length. So the layers, we call it a 3-layer bar. So our standard launcher is 1.5 inch ID. So here we have our standard system is 20 millimeters or 19 millimeters actually. In the English system, it's roughly 3/4 inch. So we have a 3/4 inch solid bar. Then we have a intermediate tube that has the same cross-sectional area as a 3/4 inch bar. And then the outer tube again has the same cross-sectional area. So what was interesting is it really met these, your diameter changes kind of control your response. So if you don't want to see a whole lot of ringing and reflections, the impedance of this joint and the contact of that joint and the tolerance control across that joint is very important to the quality of your signal. So again, we took something that's equivalent, 51 inches long, we packaged it in 18 inches of length, and we, launched it out of our launcher. So here's the result after some iteration. This wasn't our first pulse, all right? So you see, again, this is a compression striker. So you see your Gibbs phenomenon. Here's your actual threaded intersections. The only reason I know this is because I've looked at a lot of these, but at about 200 microseconds and 400 microseconds is where our threads were. So we spent a lot of time and effort modeling those regions to actually get a pulse as clean as this. So again, we took something 51, scaled it, shot it at 18 inches to make that work. We did a lot of FEA down at Mississippi State. Trey Leonard was the grad student there. So we played a lot with the slot and the geometry of the end of the striker bar. So this rounded end and this gap are things we were interested to see how the wave reflected off of those interfaces with this particular waveguide. So we played with square ends. We played with the width of the gap, and we saw interesting phenomenon in the simulated results. And what I guess the most impressive thing was we actually saw when we changed this geometry, we saw this intersection, which is what we're modeling here. We seen stuff flip from one side of the curve to the other. So we're like, wow, there must be a zero in there somewhere. So we were able to physically show the the difference by changing physically. So this is the modeled gap, this 0.25 millimeters and this 1.5 millimeters. We're able to show the difference in our, this is a simulated result in Abacus. We're able to show in a modeled results and then correlate that to our test results, which was very impressive. So what we did is we played with the thread clearance and the thread length. And so our joints, again, we're using a threaded joint. We used an insert because just to get from one diameter to another, instead of trying to bulge the bar. We tried bulging the bar, we welded and that sort of thing. But to maintain mechanical properties, we wanted to stay at the 300 KSI strength across the threaded joint. So again, this is tubes threaded together. You know, here's your middle bar, intermediate tube, outer tube, and then in between them all, we built these inserts to basically experiment with the gap between the thread roots and the thread crests, as well as the clearances. So it was a pretty interesting platform. It revolved some skill on the machining side, but it was very exciting because we were able to, you know, basically change one thing and come up with oops, sorry, what happened there? We were able to be able to show physically an inner model what's happening. So this is the last slide this year. Sorry, this was a gap study. So we did a no gap and a gap. And you notice in the no gap, we have we'll just call this more tension-y pulse, right? Where we had a gap, this 0.25 micron gap, we showed more, you know, negative off the base curve here. So the gap we want is somewhere in the middle, which is good. We were thought we were going to have to be real tight. We tried soldering these joints and everything else, but at the end of it, basically we realized if we hold a tight gap, we can actually not show these reflections in our waveguide. So again, so what we did is we played with the length of the thread. So we held the pitch constant, and we went from 24 threads down to 8 threads for a 300, basically a 30-inch equivalent bar length, 3 tubes, right? And you see the 24 thread, you see the 16 thread, you see the 12 thread, and then you see the number 8 threads, and it flips the other way. So you can kind of guess how many thread lengths we ended up going with. It was about 10.5, which basically evened out this curve to come flat across here. So it was, again, interesting result. We were able to show that in modeling at Mississippi State with Trey's work as well as our own. So again, just to reiterate, we took something that was, you know, over 4 feet long or a meter, 1.25 meters, and shrunk it down into 18 inches or less than a half a meter with some preliminary work. And we're able to generate 510, half a millisecond pulses, which is very important to do in the mid-range work that we want to do. Again, here's a simulation for the blue curve is our actual model. The simulation has the higher frequency on top of it for our final result. So very, very interesting work. After we did this, we actually we actually have a long Hopkinson bar system here at REL. So we took some magnesium, which is, kind of rate sensitive, some ZEK, and we just tested it with a serpentine striker and then basically a solid striker, both that have the same acoustic length, and the results laid, right on top of each other. We just wanted to make sure we weren't going to be able to see a difference in the material response. So you can see we did two tests of each, solids and then the serpentine strikers, and they're all at about 2000. And when I give a strain rate, that's the average strain rate over the length of interest. So where we're going with this technology is we're developing incident bars, transmission bars to basically commercially package a 30-foot system into 10 feet. So are basically, if we can do 3 folds, which is kind of our physical limit on concentric tubes. We're experimenting with 4, and we have one system right now with 5, but getting the strength on those 4th and 5th threads is being proven to be a challenge. But we're basically trying to come up with a commercial system to do high strain rate testing, you know, in that 10-foot long window. So basically we need those 500 millisecond to 1 millisecond long input pulses that we can apply load to structures. So again, I'd like to thank Mississippi State and then the gentlemen and ladies working there as well as here for putting the time in for this work. It's pretty exciting from a commercial equipment standpoint. So thank you for listening.
Great. Thank you very much, Josh.
Any questions?
Yeah, George, this is Dr. Mohammed speaking here. Thank you for your presentations. Just, I'd like to ask you about the chamber, about the temperature. What the highest temperature can reach and how can sustain that temperature for a period of time? Yeah, so we have a couple different ways we control temperature on our sample. Let's see, I don't know if I have any pictures here, but we have a we use, in fact, we have a system going to TII that uses a air system. So we mount our sample in between our bars. So I'll show this, right? So we'll heat our sample in situ with the test. So we'll use a hot air test. We can go from -60 to +250, I believe, or +225 Celsius. When you want to go higher temperature, you have to take your sample and heat it, you know, in an oven and then transfer it to the system. So for compression, that works well. We have a flame tester where basically we can heat our samples in position and then engage the bars and do the test. But if you have a lot of time where you have to thread samples together, you do lose a lot of temperature. So we have very accurate temperature control from -60 to +200, which is good for your polymeric samples. When you want to get above that, we're pretty good in compression because you can engage the bars quick. In tension, we do our heating, you know, basically on the bars itself. So you got to be concerned about the damage. So it's always the external heat is always a challenge. But like I say, with our, you know, we call it a model HH1000, you can actually let your sample soak long enough and then do the test while it's at temperature. So thank you.
Any further questions?
Yeah. Yeah, following Dr. Talaji's question, Josh, you know, this temperature chamber, you have a chamber, you have to accommodate samples. So you don't need to preheat. Do you need to? You said you do the preheat and then put it into the chamber, or what do you mean preheat?
So what we do is we put the sample, this whole bar system, right in the chamber. So basically these bars fit right through the chamber wall, and you're heating up everything in the chamber. And that's from a -60 to 225. So you won't alter the mechanical properties of your bars at that temperature. As soon as you want to go up to 800 C with metallic samples, that's where you gotta take your sample, and you can't have your bars in that kind of temperature. You'll start to draw the strength from your testing bars. So that's where we have to bring our sample from a chamber to our testing system. When you're in at 800 to 1000 C for some metals, and especially armor materials, that sort of thing is very, you know, that's like the highest temperatures we see in our.
But when you bring out your sample from say 700, 800 degrees C, and you get temperature dropped very quickly, right?
Correct. So you
and also, how can you know, assemble your tensile sample to fix with those bars? You know, this instant and also a strike and the instant bars. So that takes time, yeah.
Yes, it does. Yes, it does. So that's the challenge with doing temperature tests up that high. You can't put your samples in the heating or cooling chamber. Yep.
So you I mean, I assume you have sensors inside the chamber. So even though you bring out your samples from very high temperature down to testing chamber, your sensor can still read the real temperature. Or
Yes. Yes,
okay.
we read the real temperature, so you know what temperature you did the test at. Yes.
Okay. So your sensor actually not just from -70 to 250. So much, it's wider range, yeah?
Oh yeah, yeah, for sure. So we have different, like I say, we have the different systems for minus 60 to 200. That's one system. To go up to 1000 C is a totally different system.
Right. Okay. And for your your striker bar and also your instant bars, I mean, after many numbers of tests, I mean, I'm just wondering, do you have a kind of lifetime or what duration, say after meeting, and I don't know, say 250,000 of strikes after. I mean, those you need to replace. How often you need to replace those two bars?
So what we do is we sell what's called a bar end conditioner. So what happens in a situation, you have fatigue of this surface on the ends, your impact zones, especially from your pulse shapers and that sort of thing. You can actually dent those. We actually have a bar end conditioner, we call it, which mounts on the same system. So you basically chuck these bars up and you polish them back perfectly flat again. So you can actually spin your bar right in the, I don't have a very good example of this, but the bar that's in these holders right here, you actually use the same holders used for your test. You turn it and you polish your interfaces so that you can actually, maintain the correct test surface or the impact.
How long you need to do it? I mean,
Well,
how many strikes after?
Yeah, well, it depends what you're testing. So if you're doing with pulse shapers, with copper pulse shapers, we've done up to, I don't know, I'm going to say thousands of tests before we've
Right.
conditioned bars. If you're using an abrasive pulse shaper or you don't have very clean environment, and you're a lot of rock testing, we've actually seen like tens of tests before you got to condition the ends of your bars.
Right.
So you'll see that in excess reflection in your pulses. So, before you do a test, we always, recommend that you put all the bars together and shoot it just to test all your interfaces. And if your bar ends are, call it
But
dirty.
this kind of maintenance requirements is in the manual, yeah?
Yes. Oh yeah, definitely.
Okay. Thank you.
Yep.
Thank you, Joshi.
Yep.
Great. Any other questions before we finish? Thank you very much, Josh, for that very interesting talk there on your equipment. That was very good. Thank you.